velocity. So the angular velocity and the angular displacement of something that's rotating. What was the angular displacement generally more often known as? If you've got something that's turning like that, what up until now have you called its angular displacement?
Meters.
The angular displacement.
Is that omega?
Right? Omega is the angular velocity, but the angular displacement, the angle which it describes, is just the angle, theta. So angular displacement, if you're asked about angular displacement, all you're being asked is the angle sort of, well, so many what? What are the units that we're using for angular displacement? Asked what were the...
Before, now.
Just now, yeah.
Radian.
Yeah, so we're using radian measure, where the angle in radians is the length divided by the radius. Obviously, the bigger the length that you go round, divided by the constant radius, the bigger the angle that you travel. So that was angular displacement. Angular velocity was just the rate at which that angular velocity was changing. So the faster something spins, the bigger omega, the bigger the angular velocity. Now you can have two bicycle wheels, which operate at... So the bicycle wheel here is going at a particular angular velocity, and that linear distance that's being travelled, the linear distance L, is related to the angle that's travelled by multiplying by the radius. So that's the equation that we had. L, the distance travelled, is equal to the radius multiplied by theta. Okay. If we compare, say if this went through 3 radians of angle there, what would the distance covered by that wheel be compared to the, if this covered 3 radians? Yeah, so this is going to cover a lot more distance in the same angle than this one does, because it's got a bigger radius. Distance is equal to r times theta. How about when this one's going round at, say, 4 radians per second as an angular velocity? How does the linear speed of a point on the surface compare to the linear speed when this is doing 4 radians per second? Okay?
Slower than small.
Yeah, okay, so you're going slower, so that an ant trapped on the tyre on this tyre is going to be going a lot fewer meters per second, linear meters per second, than this wheel here. So the poor ant stuck on this tyre is going to be flying around about 20 meters per second compared to this one here. So the bigger the radius, the greater the linear speed. So if you take 2 wheels which are going at the same linear speed, so say I'm on the 700mm wheel and my poor son's on this wheel here, we're both going along down a hill at the same speed, which of the wheels is turning at the greater angular velocity? Angular velocity now. Which would have the bigger omega? Yeah, so this one's going round and round with a much higher angular velocity than this one here. In terms of friction in the bearings, which one's going to have the greater friction? Yeah, that one, because this one's going round and round, so the bearings are having to do a lot more work, which explains something about bicycle wheels.
The bigger they are, faster.
Well, the bigger they are, the fewer turns that the hubs have to go through, so the less friction you've got from your bearings. That's generally why bike wheels are as big as you can make them, apart from the size of the human frame. So that's why we generally try to use big bike wheels. What do you think the relationship is between angular velocity and the linear velocity as a point on the surface? So linear, remember, is the speed, basically. Omega is the angular velocity. How do you think the two are related? Remember what we're saying, the bigger the wheel, the greater the linear velocity, the linear speed. The smaller the wheel, for the same omega, the smaller.
Is it directly proportional?
Directly proportional, it is. Directly proportional to what though?
So the linear velocity is directly proportional to the angular.
It is, and what's the constant between the two? We're saying that as you speed this up in terms of rotational motion, in terms of angular velocity, that the linear speed changes, but what's that constant between the two? The radius. Okay, so you got the radius. So can we actually just put in as a constant that whatever omega is, if you multiply it by the radius, then obviously the faster you're going around the linear speed on the outside of the circle. So that equation that the linear velocity v is equal to the angular velocity omega times the radius is one that you actually have to be able to not only state but also derive. And it's a dead easy derivation. So have a go at that, and then we're going to do the equations of motion for things speeding up, slowing down. So linear velocity. So if something describes an angular displacement theta and travels a length L, L is equal to r theta, and that's purely by the definition of 1 radian. If you've got a radian is theta, then but because the rate of change of the linear distance here is defined as being the speed, if we differentiate both sides with respect to time, so differentiate with respect to time, then dl by dt is equal to dr theta by dt. dl by dt is just the velocity, the linear velocity v. And because r is a constant, the radius of something moving in a circle doesn't change. Well, otherwise it's not moving in a circle. Then we've got r times d theta by dt. You don't look really lucky. Never mind. Okay. So d theta by dt. What is d theta by dt, Gregor? What if you take the differential of angle? Oh, it's the rate of change of angle. What was that? It's the what? Well, what's the symbol for? It's the rate of. It's really how quickly that angle changes. Everybody's trying this sort of look now. It goes down quite. Eh? It is, yeah. Okay, so you've got omega. By the definition of omega, d theta by dt, so we've got that v equals r omega. And that, if you've got omega in radians per second, and you've got radius in meters, that's going to give you the speed in meters per second. So that's a very useful conversion factor between if you know what omega is, then you can get the linear speed at any point on the circumference there, or if like a wheel is traveling in a linear direction, if you know omega, then you know the linear velocity of the wheel. So let's just see what would my bike wheel is a 700 millimeter wheel, which means that it should have a distance of from there to there of 0.35 meters. I was coming in, I clocked myself, the fastest I was going this morning, because it was only a Thursday, was at 18 miles per hour. We'll need to do a conversion from miles per hour into meters per second. From the meters per second, you should be able to work out the angular velocity of my wheel as I was coming in this morning at 18 miles an hour. Let's try it. Okay, so. Yeah, 1,600, or if you're being exact, 1,610. So this. So from that, you should be able to convert miles per hour to meters per second. Once you've got meters per second, use that to get omega and find out the angular velocity of a bike wheel. So you should get an answer of, Andrew, what was it working out at?
23.
Yeah, 23 radians per second. And that's obviously me with a nice big bicycle wheel. You can imagine if I had my 6-year-old son behind on a rope with a bike. I mean, I'm not suggesting I'll just drag him along the ground, but if you had him just sort of dragged along on the bike, his wheels obviously be going around a lot faster and probably smoke coming from the bearings, things like that. But it's not the kind of thing I do, honest. So we've got 23 radians per second as omega in that case there. In any thing that you've got an angular velocity increasing or decreasing, you're going to have an angular acceleration. An angular acceleration, alpha, was the rate of change of omega with respect to t. Now, it doesn't take a leap of imagination to realize that if the distance that something travels linearly is equal to r theta, and the linear velocity is equal to r omega, how is the acceleration going to be related to alpha? R alpha. You're having a great day today, Donald, I can tell. Okay, so we've got the linear acceleration of a point is actually equal to the angular acceleration multiplied by the radius. All of these three you need to know. This one you need to be able to derive, which is why I've shown you the derivation. You don't need to be able to derive A equals R alpha. It comes up very rarely, so we'll just leave that. But it is something that is in the study guide that you will need to know.
What's alpha?
Alpha is the angular acceleration. It's how the angular velocity changes with time. It's the rate of change of angular velocity. Just in the same way that linear velocity increases, so the angular velocity changes. I always like derivations that start off with consider a rotating object. You can see people sitting there thinking, a rotating object, and really sort of considering it. But it's just the sort of physics speak that we're going to do a derivation about something that's spinning. So here's something which is describing an angle theta. It's going from there to there. And it starts with omega 0 as the angular velocity. And it ends up with omega 1 as the final omega velocity, the final angular velocity. It does all this over a time t seconds. And it's covering that angle theta. And the angular acceleration is alpha. That's our angular acceleration, how much this omega is increasing. So that's the setup. See if you can write down what would be the three equations of angular motion working back from what we know about linear motion acceleration equations. Can you make up the ones which would have these 5 things in it? So a couple of minutes to try that. What are they? So the 3 equations that you should have, let's see, Alistair, what's the first one that you had there?
First equation.
Yeah.
Omega equals omega naught t plus alpha t squared.
Was that omega or theta?
Theta.
Yeah, sorry. Okay. So theta is omega naught t plus a half alpha t squared. And that's obviously the same as s equals ut plus a half at squared. And another one that you had, Stas, what was the... alpha theta. So omega 1 squared, the final angular velocity is the initial squared plus 2 times the alpha, the angular acceleration, times theta. So that's very similar to v squared equals u squared plus 2as. And lastly, Jonathan, what did you have as the third equation of motion? And that's just the same as v equals u plus at. So omega 1 equals omega naught plus 2 alpha t. So those are going to be 3 equations of angular motion.